Okay, I think we can begin. This year we have 2 Mondays that will close due to public holidays, national holidays, and I have wrote this announcement. So that is the reason I have scheduled this additional course for lectures, otherwise I cannot cover all the required subjects. Okay, I will just maybe close the window because it's too loud from the street. Maybe you can also close this one. Okay, so just to repeat where we stopped last time. The last time we started with the idea of high rate approximation or high rate coding theory. And that means that instead of using the actual PDF of the process being quantized, we will somehow sample this PDF, and we will sample it exactly in the middle of quantization levels that we are using for quantization. So just to have a figure, do I have any figure here? No, back on the other side. Do I have? So the idea is to evaluate the probability density function of the process exactly at the center of the quantization step. So the value that is used to restore or reconstruct the signal value. So at this value, I will sample the PDF. And that is obvious from the expression that we have here. So for one quantization level, for all the values that correspond to this quantization step, I will approximate that PDF is constant and it is equal to the central value of PDF in this quantization step. And such simplification is necessary to avoid integration that otherwise we have to do when computing the expected distortion or when computing the entropy. For the entropy, we simply have to compute the probability of each interval, of each quantization symbol. Okay? And we have already shown the final expression that we come up to based on this approximation. And this final expression relates the entropy of output indices and distortion. That is exactly what we wanted to determine. So what is the relationship between the rate? This here is the rate, and this here is the quality or distortion. Distortion is directly determined by the step size of uniform scalar quantization. So squared step over 12, and we substitute this into this logarithm, and we will get this relationship between the rate and the distortion. And this offset term, this h of x, is actually determined by the so-called differential entropy of the process. This is something that we have to compute. It depends on the statistical properties of the process on its PDF. And according to definition, this the differential entropy is defined completely analog to simple discrete entropy by having this PDF or probability times log of probability. But now instead of summing these discrete symbols and corresponding probabilities, we are integrating along the real valued process x along its value for all of the range that this process is existing. PDF is different from 0. So theoretically from minus infinity to plus infinity, because if this fx of x is bounded to some interval, then automatically this range of integration is bounded to the span of x that is actually fx different from 0. Okay, and this definition is nothing else but the expectation of the negative logarithm of density of the signal. So this is the definition of this differential entropy, and it is required in order to have this offset term between output entropy and this logarithmic distortion. Okay. And now, from this equation, we can also derive the curve that defines SQNR, because this distortion can also be expressed through decibels by simply taking SQNR would then be 10 log 10 of sigma x squared over this d. So I will use this expression and rearrange or rewrite this equation, and I will come to this linear function that says that this SQNR is the same as before, simply 20 log base 10 of 2 that multiplies the output entropy, h of I, and now we have this offset term, SQNR 0. And that means that will be the SQNR for the case when the output entropy is 0. So if you have 0 bits over the channel, then the SQNR would be this value, SQNR 0. This SQNR 0 is then, by combining this expression and this expression here, this one and that one, this SQNR 0 can be computed as such. So it depends on the SQNR 0. It's 20 log base 10 of, now we have square root of 12 sigma x squared times 2 to the power of minus output entropy. So this is the expression that defines this offset. If I plot it, so I would have something like this. So I would have parallel lines. All these lines have exactly the same slope. And the slope is, for 1 bit, b plus 1, and this is 6.02 decibels. But this SQNR 0 is actually the value where this line crosses y-axis. So for b equal to 0, And we claim that this SQNR 0 is defined by two terms, by the signal variance and by the this is h of x. Sorry, this is differential entropy, not the output entropy. Differential entropy. So differential entropy of the signal and signal variance combined, they define this offset. But to be honest, we will show later on in the derivation that this sigma x squared also exists here. So it will be cancelled. Finally, we will show that this SQNR 0 only depends on the type of the process, not on its variance, because otherwise it wouldn't make much sense. Let's go further and we will show this in the actual examples, how this is cancelled. Okay, so let's consider first the influence of this SQNR 0. Greater the offset, we have the better quality for the same output entropy. And therefore, it is obvious from this expression that for processes that share same variance, if this sigma x squared is, for example, unit variance, then we see that differential entropy affects the SQNR 0. How? Because this is in the denominator, 2 to the power h of x. If I have greater differential entropy, I have larger denominator, and that means that this SQNR 0 goes down. So we have a lower quality for higher differential entropy. It is written here in the opposite way, so lower differential entropy automatically implies higher quality. Okay, so that is the reason why we can say that this differential entropy is somehow a measure of complexity for quantization. So how complicated the process is to be quantized with scalar quantizer followed by entropy coder. Okay? And now what we have to find is how to find the actual quantization step. That is a parameter of the quantizer, of the AD converter, of this quantizer that we want to design. We want to design a quantizer with step that I would have the desired output entropy of indices. For example, if my channel capacity is limited, is given, so the rate must be above this output entropy H of I, or in the worst case equal to the output entropy of indices, channel capacity, expressed in bits per second. And I will substitute this channel capacity here. This will be determined by the process. And from this, I will easily find the delta. So from fx of x, I can compute what is the differential entropy of the process. And this H of I is defined by the channel capacity. So from these two, I will get the required step size delta, or the smallest step size delta that ensure the output entropy that is still at least equal to the channel capacity. Okay? So how to determine the required output entropy and the step size of the quantizer if I specify given quality? That is the other way. So this idea, this concept was, if I know the channel capacity, then I would do something like this. But if I want to achieve given quality, so how then? Again, based on density, we can calculate differential entropy to determine the offset of this linear relationship between the entropy and SQNR. So first we compute this SQNR 0 term, this offset term, from the signal variance and its differential entropy. But as I said, this sigma x squared will be cancelled with the term coming from differential entropy. Okay, and then when I have this SQNR 0, I can compute from the original equation, this linear equation, what should be the required rate to achieve this desired quality SQNR minimum. So this here is nothing else but the inversion of the linear equation here. So if I want to express this required rate for the desired quality, the only thing I have to know is what is the offset between these two terms. And this offset, as I said, is determined by differential entropy and by the signal variance. Okay. So once I have this H of I, now I can compute the step size. Because you have this expression, that this step size is simply 2 to the power of differential entropy minus output rate that I have just computed. So just to repeat, I start from the signal, I compute differential entropy. Based on this differential entropy and signal variance, I compute the SQNR 0 term. Once I have SQNR 0, I can find what is the required output rate, what is the required output entropy of indices. And once I have this H of I can substitute it into the expression for the step size, and I have the required step size to achieve this quality SQNR minimum. We will also have this expression on one cheat sheet that can be used for when doing your exam. So it is one A4 simple printed page, and it has all of these main equations, so you don't have to remember them by heart. Okay. Now going further, we will show in the one simple example how we can apply these theoretical equations, this theory, for several processes. And we will start from the most simple process from the uniform probability process. Okay. So it is something like this. So this is fx of x. But now I will express this range based on the signal variance. Because if I know the range, I can compute the variance or the other way around. If I know the variance, I can reversely find the range of the signal. So this signal is different from 0 from the range 3 sigma x squared minus 2 plus square root of 3 sigma x squared. Okay? And of course, then the density, the height of this square must be equal to 1 over square root of 12 sigma x squared, such that the area is equal to 1 unity. Okay? So that is the density that we are starting from. We already had the same example before, but before we had some concrete range. For example, from minus a half to a half, something like that. But based on the range, then later on we have computed what is the variance. Now we start from the variance. Let's say the variance is defined, sigma x squared, and based on the variance, then of course I know what should be the range of signal with uniform distribution in order to have this desired variance sigma x squared. So this is the probability density function PDF. We can also plot PDF. We can also plot the cumulative density function, and it starts from 0 at this point and goes to 1 at this point. So this is 1. So this here is cumulative density function of x, CDF of x. It is simply the integral of PDF from minus infinity to x. So that is how it is defined. And if I write it in using expression, I can have this linear function defined by this simple expression. Okay. So for x that is within the range, this is the expression for this line. So starting from 0 value, so 0, it's argument minus square root of 3 sigma x squared, because this is cancelled for the left edge. And for the right edge of the interval, when I sum up these two values, I get exactly the same value as in denominator, which are cancelled. So I get the integral with CDF of 1, what should be exactly what I am expecting on the right edge of the uniform distribution. Okay, now that I have these two, I have PDF and CDF, I can now try to compute this differential entropy from the signal PDF. And according to the definition, this signal entropy is then, as I said here, the integral of such PDF times logarithm of PDF. Since PDF is constant in the range between this left bound and right bound, I can extract this constant value, 1 over square root of 12 sigma x squared, in front of the integral. I can extract also the logarithm of the same density in front of the integral, because the logarithm is also a constant value. So the only thing that is left inside the integral is simply dx. And dx integrated in the range from the left bound to the right bound of the density. Okay, we now show this derivation. Okay, where it is? Here. So this integral is simply reduced to the integral of dx from the left bound to the right bound. And in front I have the extracted density, 1 over square root of 12 sigma x squared, and times logarithm of density. Okay? Because it is negative logarithm of density, and this minus sign is also cancelled. And when I simplify this, or when I compute this integral and cancel what I can cancel, I have this final expression that this differential entropy of signal with uniform distribution is logarithm base 2 of square root 12 times signal variance. Okay. So that is the final result that we are trying to find. And this differential entropy is expressed in bits if I use logarithm base 2 here. Okay? Now that I have this age of x, I can compute S squared R0 using the expression that I have written before. So this expression here, this S squared R0, is used to find this linear offset term that I'm trying to estimate, let's say, I'm trying to find. Okay? Now it is only written slightly different because if I extract this square root in front of the logarithm, okay, so if I take this to the power of 1/2 in front of the logarithm, then it comes to 10 logarithm 10. But by extracting this 1/2, I have to multiply this term by 2. So it is 2 to the power of 2 times differential entropy. Okay, but this is the same expression as shown on the whiteboard, but only with this 1/2 extracted in front of the logarithm. Okay, now I will insert this value here for age of x into this expression for S squared R0. And I have 2 to the power of minus 2 logarithm base 2 of square root blah blah blah. And if I simplify this expression, if I write it on the whiteboard, 2 to the power of minus 2 logarithm base 2 of square root 12 sigma x squared. Okay, sigma x squared. So that is nothing else but 1 over 2 to the logarithm 2 squared 12 sigma x squared and then squared. It is the same thing. So the squared value of the denominator. Okay, and I know that this here is nothing else but sigma 12 sigma x squared square root. And then when this squared and square root are cancelled, I end up with only this term here, 12 sigma x squared. So this term here is exactly equal to this term here, but in the denominator. So these are cancelled, and what I get is unity, 1. So I get that this S squared R0 offset is 0 because it is logarithm 10 of 1. Okay? And that is something that we were expecting, because even before, without the assumption on high rate, we have shown that for processes uniform distribution, we have 0 offset S squared R0 between the quality and the rate. Okay? But now we have really proved that even with this high rate assumption, this still holds. Okay. Now we can find the required step size for the uniform quantizer. And for that, we only have to decide on the rate. So this age of y is selected or chosen as general rate, available general rate. And this term here is 1 because we have 2 to the power of 0, so this vanishes. And the only thing that is left is this second term, 2 to the power of minus h of I. And no, sorry, I'm wrong. So this here, 2 to the power of h of x of the process. So this is differential entropy of the process. We have already computed this term in a similar fashion. So this was 2 to the power of, where they have it, exactly this term, 2 to the power of logarithm, this is differential entropy, 2 times differential entropy. So the only difference between this expression and the one written here is this squared value. So instead of having this squared value at the end, I have now without the square. And the other difference is the sign, because here I had the negative sign, now I have positive sign. So what I expect that this first term, 2 to the power of differential entropy of the process, uniform, is then the same as before, but now I have the square root, and this must go in the numerator because I have different sign. So it is simply square root of 12 times sigma x squared. So that is the first part of this final expression. The second part is then 2 to the power of desired output rate minus h of I. And from this expression I can find the smallest quantization step size I can use to still have the rate that passes through the channel. Okay? Now we will show also another example that is a bit more complicated, so we will not go in details of derivation of these expressions shown here, but I will just shortly discuss them, explain them. So the process that we are now deriving, or the expressions that we are now deriving for the process is normal distribution or Gaussian distribution. You have definitely, hopefully, so far get knowledge of this Gaussian distribution or normal distribution. So it is this exponential that has the parabola in the argument of exponential function. So this is nothing else but negative parabola. And if I take this exponent of this negative parabola, I will also have a normalization term that ensures that the integral of this fx normal is equal to unity. So this is just a normalization term to be that gives desired density that must be integrable to 1. Okay, so this is normal distribution. Do I have a plot? No. No. We will have it in Markov simulation. Okay. So starting from the normal distribution, we can also use our textbooks and find what is the CDF of the normal distribution. So the cumulative density function for normal distribution is defined by the so-called error function. This error function is defined using this integral, quite nasty integral. And once I have this fx and phi x, I can try to compute differential entropy the same way that we have done for the uniform process. But the main difference now here is that this integral is not in the finite range that was from the left bound to the upper bound. Now the integral is from minus infinity to plus infinity, because this density is defined on the whole range of real values from minus infinity to plus infinity. Okay, so first we start with differential entropy. I can extract only constant part of the density, and this constant part of the density is this term here. I can extract it in front of the logarithm. Now I have this function of x part of the density still within the integral, and I have logarithm base 2 of the density integrated over the whole range of real values. Okay. Now I can also extract this constant here in front of the integral. It is something like this. I don't know. Have I done it? No. No, not yet. Now I have just changed the base of the logarithm. Okay, because I want to cancel the exponential function with logarithm function. But I cannot do it because I have the logarithm base 2 here, and I have exponent base e here. So to have the same base, what I have to do, I have to change the base for this logarithm, and I do it by simply using the identity that logarithm base 2 of x is the same as ln, or natural logarithm of x, but divided with ln of 2. So that is the source of this ln of 2 that comes in front of the expression. And now I have changed this second part. It is now logarithm base e, so natural logarithm of this term here. So the first part is simply natural logarithm of the constant term, minus 1/2 due to the square root and due to being in denominator of this argument, 2 pi sigma x squared. And the second term is then simply plus argument of the exponential function, because the exponential function is cancelled with natural logarithm. So I have minus sigma x squared over 2 sigma x squared. Okay? And now I have to integrate this over the whole range. Actually, now I have two terms. I have the first term, this times this constant, and I have the second term, this times x squared over some constant. Okay? And I have to compute these two integrals independently. And it is done on this slide. So we'll now go only to the final result. So the first part is trivial because it is nothing else but the original density, integral of original density of the process, and I know this should be unity. So that was from the first part. From this part here, when I compute this integral, I will find this integral to be 1. For the second part, it has this form, x squared times the exponential function of the kernel of Gaussian density. And this here is more complicated to compute because the second term here is finally square root of 2 pi sigma x to the 6th power. So the integral of this second term. Okay, and finally I can combine both and to find the desired differential entropy h of x. Okay, when combining these both terms, first and second, and after simplification, I will end up with the final expression for the differential entropy for normal distribution to be 1/2 logarithm base 2 pi e sigma x squared expressed in bits. So at the end, this is a rather simple expression. The derivation was a bit complex, but the final expression for the differential entropy is rather simple. Again, it depends on the signal variance sigma x squared, because this is required, so otherwise this sigma x squared would not be cancelled with the same sigma x squared in the expression for SQNR 0. Okay, so now I use this h of x to find this offset term of the SQNR curve, and again, after simplification, after substituting this value instead of h of x normal, I will find out that at the end it is a constant term. It does not depend on sigma x squared anymore. Sigma x squared is cancelled here. I have a constant term equal to minus 1.53 decibels. So I have found that the offset between the SQNR curve and rate, h of I, is SQNR 0, which is actually negative, minus 1.53 dB. And remember that for the uniform distribution, this offset was 0. So what I see that for the same output rate, if the input process is normally distributed and not uniformly distributed, I would have 1.5 dB worse quality. The quality would be lower. Okay. Finally, I can also express what is the required step size for uniform quantization of normal process, and it is this expression here. So it depends on the output entropy of indices that I can pass through the channel, and it depends on the signal variance sigma x squared. Okay, in conclusion, this normal distribution process has 1.53 dB higher distortion or lower quality than the uniform distribution, and that is exactly due to the fact that the required step size for the same output entropy in comparison to the required step size of uniform process is 1.19 times larger. So I cannot use the same step size as for uniform process of the same variance. I have to increase the step size to still have the same output entropy. So because the quantization step must be 1.193 times larger to get the same output entropy. So that is the reason that we have this higher distortion, 1.53 dB higher distortion, due to the larger step size. Okay, and as a final conclusion, it says here that it can be theoretically proven that the process of normal probability, Gaussian density, is the most complex for entropy-constrained scalar quantization of all processes that share the same variance. So for all processes with equal variance, the process with normal distribution is the most complex process. I will get the least quality for the same output rate. Okay. So for a process that have unknown PDF function, if we know only the variance of the process, we can use this normal distribution as a lower bound for the quality. It cannot be worse than for normally distributed input process. So for any process, differential entropy is smaller than the differential entropy of Gaussian process. So this term here is what is the differential entropy for Gaussian or normal entropy. So for any other process, the differential entropy should be lower, meaning that the process is easier to be quantized. We will end up with higher quality for the same rate. So this can serve as an upper bound when designing a quantizer. Okay, and now we will do the example prepared in MATLAB, but since it is only 5 minutes to the break, we will do the example after the break. So now if you have any questions regarding this theoretical part, this is a bit more demanding, but nevertheless the final expression is simple, and you will have this final expression on the cheat sheet for the exam, and you can use them. Okay? So the final expression would be that we'll have 3 processes that typically we use for the exams: uniform distributed process, or some maybe piecewise constant, but not uniform, something here, something there, and Gaussian process with expressions that are given in the cheat sheet, as well as a process that is simply sine signal. We will have it in the example. So if the input signal is sinusoidal or cosine signal, then I can also compute what is the fx of x of such process. It is not uniform. We will see that its density of such a signal is not uniform density, although one might expect that if this sine value goes from -1 to +1, I will have like a uniform density between -1 and +1. But we will see that this is something unexpected. We will have the density that goes to infinity on the edges, on the value of minus amplitude, plus amplitude. After the break, when we do the actual example in MATLAB. Now, let's have a break, if you don't have any questions. and we will start 10 minutes past. Okay, now I will first walk you through the code, in MATLAB code that I have on the presentations. Okay, just to explain what we can do now with this program, what we will do. Example 2, okay. First of all, the same as before, we defined the interval for the time indices, n, 0 to caps n minus 1. We then choose a random frequency. This random frequency is something between 0.1 pi to 0.9 pi by using random generator in MATLAB. Once I have this random frequency, I will construct a signal depending on the choice of this variable sig. If it is 1, I will create a sinusoidal signal. If it is 2, I will create a random signal with normal distribution and unit variance. So the second choice is exactly for the example that we have derived lately. So the idea is that I simply create a random signal of the length n that has unit variance and PDF according to the normal distribution. And finally, the third signal would be a triangular signal, hopefully. Or no, sawtooth signal. So like a linear up, vertical down, linear up, vertical down. So I construct this sawtooth signal that goes from -1 to +1, also with the given frequency omega. Now that I have this signal, I will remove the mean value from the signal if there is any mean, such that I have 0 mean, and I will also normalize with the square root of variance, because this operation ensures that the variance is exactly equal to 1. So after this normalization, if I divide the signal with the square root of its variance, I will get a new signal, scale signal, that has exactly unit variance. So normalized variance to unity. Then, now that I have signal, I can compute what is the differential entropy. And these here are theoretically derived expression for differential entropy for all the three signals that we are using in our simulation. For example, for last one, this sawtooth wave signal is actually a signal that has uniform distribution, because it goes through all the values from -1 to +1 with equal probability. So that is the reason why we use this last expression. It is the one that we have derived for the uniformly distributed signal with variance sigma squared. Okay. Of course, our sigma is 1 because we have just normalized the signal, so we don't have to use it, but I have written here just to see the original theoretically derived expression that has sigma x squared in the expression. So this here is for the uniform distribution. This here is the one that we have derived for the normal distribution. So this one that we have just found out where it is for normal distribution, age of x should be this here. So 1/2 logarithm base 2 pi e sigma x squared. Let's try to find it here. 1/2 logarithm base 2 pi exponent of 1. So this is e sigma x squared. So this is exactly the theoretical expression for differential entropy that we have derived for normal distribution. And similarly for sinusoidal signal, its differential entropy is written here, but I don't have derivation for its expression, but let's say, trust me, it is correct. Okay? Now that we have differential entropy for the chosen signal variance, and we have chosen unit signal variance, now we can compute what is the required step size, delta. So this D is this delta step size, in order to achieve the output entropy of indices H. So this H is defined how many, what is the channel capacity, for example, 3 bits per symbol. And the value of h of x is computed up, and now we have the required step size. Okay, going further, since we have the step size, we can easily compute what is the expected variance of the quantization, because we know that this expected variance or variance of the error, is simply 1 over 12 times step size squared. So 1 over 12 times step size squared times, so delta squared over 12, that's to be correct. Okay, delta squared over 12. That is the expected variance of the quantization error. And now we can compute the SQNR, and the SQNR is then simply 10 log 10 of unit signal variance. This one is sigma x squared over sigma e squared, so this distortion. And we have this SQNR in decibels. Okay, so this is all of those are expected theoretical values. So the differential entropy, the required step size, SQNR. So that is something that we are expecting to observe from the actual quantized samples of the signal. Now we will do the actual quantization. So starting from this signal y, we do the uniform scalar quantization by simply dividing the signal with the step size and rounding it to the nearest integer. Once I have these indices, yi, I simply multiply the indices with the step size, and I have the quantized signal. The difference between the original signal and quantized signal is the quantization error, ER. And now I can compute what is the mean squared value of this error as an approximation of variance, error variance. Of course, this approximation is close if error is unbiased, so if the expected error is 0. And of course, the other way is that if I have sufficient number of samples. If there is sufficient number of samples, then this sample mean of squared error is a good estimate for the expected variance of the quantization error. The same way I do it for the signal. So the expected variance of the signal, what should be unity, as I know, is then found here as a mean of squared value, mean of the signal squared value, and this EY should be close to 1 because the original signal was normalized. Okay, now that I have this sample-based estimates of variance for the quantization error and variance of the signal, I can take the quotient of these two and again compute 10 log 10 of the quotient. So what I get is the actual SQNR for the choice of the output entropy H. So this is the actual SQNR. This is the expected SQNR, and this is the actual SQNR. Finally, what I have to do, I also have to compute what is the rate of the output indices. So what is the entropy, this H of I? And that is given in the next slide. So first of all, so I start from the indices, this yi. So these are the integer numbers corresponding to the quantization levels. I start from this. I take what is the minimum value of yi, what is the maximum value of yi. So what is the range of these indices from minimum to maximum value. And now I will construct a vector that contains all the codes from the minimum value up to maximum value. Okay, so these are the codes. And the function hist is nothing else but the histogram function. And it will count simply how many times have the value achieved, have the signal achieved the value of yi minimum. Okay, how many times yi minimum plus 1, blah blah blah, up to how many times I have observed in the signal yi the value of yi maximum. And this histogram is then scaled by the total number of samples such that it sums to unity. So this now scaled version of histogram is the approximation of the signal PDF, but through the histogram, because now we have discrete symbols. These yi are discrete symbols, okay? And now to find the entropy, the only problem is that I might have that probability of certain levels is exactly 0. I have not observed, for example, the value of -3. I have -4, I have -2, but I don't have -3. And if I would compute the logarithm of such 0 probability, I would get -infinity. And to avoid this, because I know that the probability of this sample is 0, so it is 0 probability times logarithm base 2 of 0 probability. To avoid this problem, I will take only those probabilities which are greater than 0. So find probabilities which are greater than 0 and use only those. So the code that exists, you use only those in the expression for the entropy, for the simple entropy of this discrete process. So I don't write here a sum, but I do the summation by multiplying a row vector and a column vector. So this here is a row vector. So PDF, so this histogram for all the codes that have non-zero probability, times logarithm base 2 of this PDF, but transposed. So when I multiply a row with a column vector, it is first time first, second time second, accumulated. So I get exactly the expression of the sum of negative probability times logarithm base 2 of probability. But you have to use this code exists, code postoji, because otherwise this logarithm base 2 of 0 would give -infinity, and you would get nothing through this summation. Okay? So this is the output entropy of the indices. Okay, and now what I also try to compute, what is the expected output entropy based on the theoretical PDF, theoretical underlying PDF. Because I know what is the PDF. For each of those signals, I know the theoretical expression that gives me the PDF of Gaussian function. I know the PDF of this uniform function. I know the PDF of sinusoidal function. It will start like this. So now I will do the derivation of probability for each of the steps. What it means, I simply have to integrate PDF in the range corresponding to the lower bound of the quantization step to the upper bound of the quantization step. I have to integrate the actual PDF of the input process in this range corresponding to the one quantization step size. This would give me the expected entropy of output indices, but for infinitely long signal. Because when we operate with n caps n samples, we only get the one realization of this random process. And this realization gets closer and closer to the underlying PDF as this caps n is increasing to infinity. But nevertheless, we can still compute what is the probability of observing certain symbol directly by knowing what is the fx of x. Because this fx of x is known analytically for all three distributions. So I know it in advance. And I can use this fx of x to compute what is the integral, or what is the CDF actually, differential of CDF, what is the difference of CDF on the right edge minus CDF on the left edge. This gives me exactly the desired area under the PDF curve. And this is done here, so I would not go into detail, but it is simply computation or finding the expected entropy of output indices for all the codes. And this value is, of course, theoretical value. It is defined only by the theoretically or analytically defined PDF of the input signal. So the original hi of I is the actual output entropy for all the codes, while this hi expected is the theoretical or expected output entropy for all the output codes. Okay? And then I will plot all of this. I will maybe just explain one additional plot. This here is the PDF. This here is the PDF of sinusoidal signal. So if I would compute this fx of x for sinusoidal signal, I would get something like this. So who can explain me why do I have this very high probability of extreme values what corresponding to the maximum negative or maximum positive amplitude? So why do I have such higher density exactly when the sign is passing through the most negative value and when the sign is passing through the most positive value? So this is, it is different from the sawtooth signal. So for sawtooth, I have equal probability for all the values. These are the outliers. I will explain later. But I have equal probability for all the values of the sawtooth signal. But for the sinusoidal signal, I have much higher probability for the extreme amplitude values than for values close to 0. So how can we explain this? It is due to the shape of the sine or cosine signal. So if I plot it, now if I count how many values I have, large values, large absolute values. So this is large, this is large, this is large. But how many values do I have that are close to 0? Maybe this one is close to 0, this one is close to 0, this one. But those that are large in amplitude, in absolute amplitude, are occurring much more often here, here, and here. So the slope of the sinusoidal signal is small here. It has like a smooth function, a very steep slope here. And for that reason, I seldomly observe values while sinusoidal signal passes through 0 because it is very steep function for that values. While the maximum amplitude is achieved much more oftenly here, so I can count how many times have I observed large amplitude value in comparison to how many times have I observed small absolute value of the signal. And this gives me exactly this curve here. And theoretically, this goes to infinity. So the density for the maximum value of the sign is plus infinity. It is something that we can hardly understand because how the probability can be infinite, but it is probability density. So you always have to take into account that it is a quotient of the histogram with the bin size. So as the bin size gets smaller, then of course this quotient might get to infinity in limit case. Okay? So the theoretical expression for this PDF of the sinusoidal signal goes to infinity at the maximum negative and maximum positive value. But of course, for value that is not exactly maximum, but corresponds to the most negative quantization step size and to the most positive quantization step size, I have some finite density. And the green curve corresponds to the theoretically derived PDF. So the green curve corresponds to the expressions shown here. They start from the analytically defined PDF of the signal, compute the CDF, compute the probabilities. So these are shown with the green curve. Okay, the green curve. While the blue dots, they are based on the actual realization with caps and samples of the input signal. And you can see that these blue dots follow quite closely the value that I should get based on theoretically derived PDF. So this is for the sinusoidal signal, for the output entropy of 4 bits. What you observe is that you have a given number of symbols. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like 21 symbols. Okay, this is written here. 21 symbols that are used to represent the sinusoidal signal in this range for output entropy of 4 bits per second, per symbol, 4 bits per symbol. Okay, just to put it in contrast with the binary code. If I would use binary code, 4 bits would give me only 16 levels. So with 4-bit output binary representation, I would have only 16 quantization levels. And this increase to 21 is only due to the fact that I have entropy coder. That the probability of these samples is much higher than the probability of those samples, and with using variable length coding, like Huffman or arithmetic coder, I could achieve compression. Since I don't have equal probability of all symbols, I can achieve compression. The same thing is for the Gaussian distribution. So for Gaussian, it follows this Gaussian or normal distribution function. It is a green curve, so this is a theoretically derived PDF, while the blue dots are those that come from the simulation, from realization with caps n samples. I think that n is 8,000, something like that. I use 8,000 samples to compute this empirical PDF of normal distribution. And again, we can see that it follows exactly the theoretically derived expression, but in contrast to the sinusoidal signal, I can observe that now I have 38 symbols for the same output entropy of 4 bits. So it is much larger than binary coding. So if I would use, for example, 5-bit binary codes, I would have 32 symbols. And this is even greater than 32. So obviously, for the Gaussian signal, I can achieve quite high compression due to the fact that the probability of individual values are quite different. So some values are quite of high probability, for example, those, and some values of the signal are occurring very seldomly, so they have very low probability. And finally, what we should get for the triangle or for the sawtooth signal, it doesn't matter, is something that is uniform. But the reason that we don't have exactly uniform value on the edges is due to the fact that the last value is twice narrower, the last quantization step is twice narrower than all of the other quantization steps. Just to somehow illustrate it, maybe we'll hear it in the simulation, but I will explain it in simulation. Okay, now we will skip to MATLAB. We will go to MATLAB. And first we'll activate this demo mode. You will use exactly this example for your laboratory exercise, okay? To do the extension of this quantization concept, but not doing the quantization in original, let's say, time domain, but in transform domain by transforming short vectors of 4 dimension into DCT domain. Okay, now I will activate first this demo mode just to show individual examples. I have selected here the output entropy. This H vector is a vector of desired output entropy. If this vector is only 1 element long, it will do only this example with 3 bits per symbol. Later on, we will do simulation for all the output entropies from 1 bit per symbol up to 16 bit per symbol to get the SQNR curve. But for the first demo mode, this output entropy is fixed to 3 bits. And now we defined sampling frequency, 8,000. Number of samples is much larger. So the realization is 100 times 8,000. So it is quite a long realization. That is the reason that we have such a good fit between the theoretically derived PDFs, blah, 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 and those that are found from the experiment, from the empirical experiment. Okay, now we define the signal, and we can first start with sinusoidal signal. Okay, and now it goes in the while loop infinitely, repeating, create one random signal of randomly chosen frequency, and do all of the stuff that I have described on the slides. So I will run it now. For sinusoidal signal with 3 bits output entropy. Why? This here is the histogram of the quantization error. Okay? Histogram of the quantization error, that is the approximation of its PDF of E, error E. These here are the signal samples. You cannot really recognize a sinusoidal signal because the frequency is rather high, so it doesn't look really like a sinusoidal signal. But if I plot it in this way, maybe you can now understand it is a sine, but after doing the reconstruction, it will be even better resembling the original sinusoidal signal. Okay, so these blue dots are original values of the signal, sampled equidistantly in time, while this green curve is the quantized value for each of the samples. And you can see that this quantized value is slightly different than the original signal value. For example, here, this is the original value, and this is the quantized value. This is the original value, and this is the quantized value. So I can see the quantization error because I have the chosen output entropy of 3 bits. And after reconstructing the signal, it has to pass through the edges of this quantization signal to the green. It passes through this edge, to this corner, through this corner. It passes through this corner, blah, blah, blah. So I have this reconstructed sinusoidal signal. Another frequency. Okay, now I will maybe change the type of the signal. Okay, instead of using the sinusoidal signal, I will now try to use random noise, with not uniform, but with normal distribution. Now I will repeat the same simulation, but with random noise. So this is the samples of the input signal, quantized value of these samples, and reconstruction. So they really sound almost identical. The original signal and quantized signal, there isn't any significant difference with output entropy of only 3 bits. And last example is for this sawtooth or triangular signal. I'm not certain, but I think it's sawtooth. Signal number 3. Signal number 3. I repeat the simulation. You can hear it is sawtooth signal. Okay. Now probably you can hear this difference, especially when the frequency is rather low, because then we have this high frequency oscillation caused by quantization, and you can hear this error for such a signal. So you hear these high frequency variations that are added to the original signal that was without this. Okay, and now that we have shown that these 3 examples for 3 types of signal, we will now repeat the experiment, but not only for one chosen output entropy, but for a range of output entropies from 1 bit per symbol up to 16 bit per symbol. Okay, I will repeat this experiment. How will I do it? I will simply set this demo mode to 0, and that means that it will activate this choice for the output entropy. It will be from 1 to 16, and I will do it first for the signal that I have just chosen, for the sawtooth signal. Now it will not play anymore the signal to the loudspeaker, but it will compute the empirical SQNR curve and this theoretically derived SQNR curve. So we have shown in the slides that we can start from the realization, from the process realization, and compute empirical output entropy, compute the empirical error, SQNR, the actual error, but also we could compute what is the expected SQNR and what is the expected output entropy. And these two curves are shown with a dark blue and light blue line, where the dark blue is the expected, theoretically derived relationship between the SQNR and output rate, h of I, output rate. So it is a linear curve, and it should pass through 0 because this PDF for sawtooth signal is the same as PDF for uniform signal. So we have shown theoretically that for uniformly distributed input signal, the offset term is 0. The line must pass through 0. Okay? But you can see that for the actual realization, I have this light blue curve that is slightly different for low rates. If the rates are low, I have this discrepancy, I have this difference between the expected theoretically derived relationship of SQNR and rate and the actual relationship between the SQNR and rate. Okay, but for higher rates, I can observe that these two curves are really coinciding. So for higher rates, the theoretically derived high rate approximation is exactly equal to the observed empirically derived relationship between the SQNR and the output entropy from one signal realization. Okay? And it is repeated for different randomly chosen frequency of this sawtooth signal. Each time when I press space, it will compute a new simulation for different frequency of this sawtooth signal. More or less, it behaves similarly. It doesn't change a lot. So more or less, it is the same relationship for all of those frequencies. Now I can repeat the same thing, but not for the sawtooth signal, but for signal with normal distribution by selecting signal equal to 2. If I now run the simulation, now with normally distributed input signal, I have even smaller difference between the theoretically expected value of the SQNR to output entropy relationship in comparison to the empirically derived. So more or less, it is practically identical curve after 2 bits per sample upwards. Okay, each time when I press space, it will create a new random set of input realization. But since the realization is very long, this realization is quite good approximation of the underlying process. And that is the reason that nothing changes each time when I press enter. Okay? But if I select the sinusoidal signal as a last example, signal equal to 1, now I have a slight difference between the
theoretical and empirical curve. It also depends on the signal frequency. So as the signal frequency is randomly chosen, you see that you have some difference between the theoretically derived SQNR and empirically derived SQNR. Okay, but more or less for 4 bits upwards, these two curves are coinciding. So the difference is only for small rates. And that is exactly what we were expecting, because this high rate approximation model was supposed to be a good approximation if the rate is sufficiently high. Okay, so that is the derivation of its name. That is the reason for its name. High rate coding, high rate entropy constraint quantization. Okay, and that's more or less what I wanted to show in this example, just to prove that if the realization is short, so for example, if I would use only, let's say times 1, shorter realization of only 8,000 samples, then you would have higher differences from one trial to another trial. For example, shown here. So something strange starts occurring at very high rates as soon as I select a short realization. Why? Because the statistics of the signal is not corresponding to the underlying theoretical PDF, because I observe only certain values of the signal. That is the reason. And that is then manifested for high rates. So for short realization. If I make it even shorter, if I use only maybe 800 samples instead of having original 800,000, if I use only 800 samples, so this discrepancy then comes even earlier. This difference between the theoretically derived output entropy and empirically derived output entropy. What you can observe is that such short realization has a finite output entropy of indices, irrespective of the quality. So it has like a bounded output entropy because I don't have the universal sample of this signal. This 800 samples is insufficient to describe its statistics. Okay? For a reliable description of the signal statistics, I must have much larger number of outputs of input samples. So the realization must be much longer, and I will write this 100 as it was before, just such that I don't have problem next time when I run the program. Okay, so if I have much longer realization, then everything is then again as before, behaving normally. So this is the example that we will be using as a template for your second laboratory exercise. Not second, for the first laboratory exercise. Okay. Okay, now I will end this. So this is done, and I will open now the next presentation because we have come to the end of this one. What we have learned what is the high data rate quantization theory, the basic idea of this high rate theory, what is the relationship between the entropy and distortion, how to find the differential entropy of the process. Then we have shown that this signal to quantization noise ratio is a function of the output entropy, but there is this SQNR0, this offset, and this offset is determined by the statistical properties of the input signal. So we have shown how to determine the quantization step size, how to determine the entropy for the given quality, and 3 examples: uniform probability density process, normally distributed process, and also in simulation a sinusoidally distributed process. So the PDF of a sine signal. Okay, and we have shown that this Gaussian or normal process is the upper bound for the entropy. So it is the most complex process for quantization. Okay, and now I will skip to the next presentation. I will quit from MATLAB. And the new topic is related to predictive coding or quantization, NT03, MS03. Why do I have to be punished? Okay, it works. Okay, so we will now go to the next chapter, and that is predictive coding of media signals. And we will introduce something that is called linear prediction as the simplest way of predicting samples of a signal. Okay, so the task of prediction is based on some vector process x, it is necessary to predict scalar process y. Okay? For example, as shown in this image, let's say that I have a vector. This is one vector with elements xy to xp. And it is only one vector of a random process. So I have infinite number of such vectors. And this is then process bold caps x. And from this process, from this set of vectors, I want to predict a scalar process y. So I have one vector, another vector, blah, 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 another vector. So all of these vectors are drawn from the random process x. So I have this random process x, this ball, and I take first vector from this process, second vector, blah, blah, blah. And again, I have a scalar process y, and I have corresponding value, only one scalar value, only one number, and this number I'm trying to predict from this vector here. So I'm trying to predict what is the expected value of this y if I know x. Then I have another value of y. Then I ask myself how to predict the expected value of this y from this vector. Okay? So if there is any relationship between these two processes, then I expect that this predictor should be able to do its job, to do some kind of prediction that gives me approximation of this y. So it will not be exactly equal to y. It will be some y whatever, ket or tilde, y tilde. Okay, I will get another vector that is close to y, not equal, but I want it to be as close as possible. As close as possible. And just to somehow illustrate this concept, let's say that the output value that I want to predict is what would be your tax return, annual tax return in 10 years from now. Okay, that is the output process that I'm trying to predict. So one day you will be hired by some high-end company, and you will have a great salary, and you will have to pay taxes to the country that you will reside. And let's say that I'm somehow trying to predict what will be your annual tax return 10 years from now. And that is this y process on the bottom. And this is what we call it in the first row, this is what we call it in the second row, blah, blah. So these are the target values that I'm trying to predict. And what are the sources for this prediction? They are hidden in this input vector. So maybe I might ask myself, does the height of a person has anything to do with its further salary one day? Maybe I can say, okay, what is this height in meters? So it is 1.8 meters, okay, the guy that is very tall, probably he will make a big money. Okay, another way, I might ask myself, what is the size of his shoes? Okay, size of the shoes. Maybe it also is correlated to your money that you will get one day, or whatever. So I can put any kind of feature in this vector that I'm supposing to be somehow related to the target value that I'm predicting. In Croatia, it will be also whether he was born in one small town that is called Imotski, that is close to the seaside, but not on the seaside, because people that are born in Imotski are usually very rich one day when they get of age. Okay, so it's like a joke. If you are born in Imotski, then you will make a big money. How to do this prediction? So how to create a predictor that is really capable of predicting the target value if the only thing I know are these elements of the source vector, elements of the source vector. So it is like a fortune teller that is predicting your future. Okay, so the goal of this good predictor is to make the output prediction, this y tilde, this green shown value, and this y tilde should be as close as possible to actual y, that one day we can really measure or observe. Okay, now we can really know what is your annual tax return. And what is the error? Error is simply the difference between the actual value one day and the one that we are predicting based on some past values of this source vector. And in this sense, it is necessary to introduce also a measure of similarity, because otherwise we cannot, without introducing a matrix, we cannot say whether it is a good or bad fit. And as a simple engineering measure of similarity that is used often in the engineering field, we will use the expected squared difference. So I know the process y. This here is the process y tilde. This here is the process y tilde. The predicted value, I take the difference, which is equal to the prediction error, and then I simply square this error and find the expected squared error of the prediction. So this sigma e squared should be a good measure whether this prediction is good or bad. And also we will assume that the prediction is unbiased, so that the expected value of e is 0. So I don't have systematic error in judging your annual tax return, such that I'm constantly below the estimate or constantly above the estimate, so I have 0 bias in my estimation. If this zero bias is true, then this sigma e squared is really good measure to say how good is this prediction, how good is it. Okay, so maybe it is now just to make a break because it is exactly 10 o'clock, and then after the break we will continue. Okay, now that we have defined the metrics and we have defined the idea of prediction, now we have to decide how to do the actual prediction. And it says here that in most general way, such prediction can be constructed based on joint or conditional probability density function between the original vector process and the target scalar process. And what does that mean? It's quite complicated written. It says here that if I would, for example, just to make it simple, okay, assume that I have a target process y, and this input process x is not really a vector process, but it is also a scalar process, x. So for input value of x1, actually I have the value of y1. Let's say that I know in advance. I know in advance pairs of such values. So for the input value at x1, I have the corresponding value y1. Then for another value x2, for example, I have another value y2. And I simply plot such dots. Dots, dot, 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 dot. So these dots, they represent statistical relationship between the source process and the target process. And these dots are a realization from the underlying PDF. So I have this fxy of x, comma, y. This is the conditional probability of these two processes, random processes, x and y. And how this PDF looks on, it is drawn, it is shown in the third axis, in z axis, as a density above this xy plane. Since this density is complicated to be drawn as a third axis, I will show the lines of equal probability. So maybe equiprobable lines are something like this. So this green is this underlying conditional probability between the source variable and target variable. And these red dots are actual realization of this conditional probability. I have some random value of x and corresponding random value of y. But these are not completely random one to another. I have some dependency between them. And this dependency is obvious from this plot, because if x is in this range, then y would be in this range. If x is in this range, then y would be in this range. So I have some statistical dependence between these two variables, random variables. And I say that I can theoretically predict what is the expected value of y if I know the actual value of x. Because if I know the x is somewhere around here, then probably I just have to evaluate this conditional probability and find its maximum. I would maybe take a cut, vertical cut of this density, something like this, at some value x0, and this vertical cut will give me something like this, some function. So this is the vertical cut of this plane, above this surface above this plane. And this has a maximum value here, y0, let's say. This is the most probable prediction for y value if I know that this x0 is something like this. I have the cut of this conditional probability. I have the corresponding density over this cut. And I try to find what is the maximum probability. So what is the y that gives me the maximum probability along this cut? And it gives me y0. So I have prediction from x0 to y0, okay? If I do the cut on another location, I will get a different function, maybe something like this. And it will give me prediction of this value, okay? this is maybe x3, gives me y3. So by simply doing the cutting of this conditional probability of two variables, I am predicting one from the other or the other way around. It doesn't really have the direction, doesn't have any importance. So I can start from y to predict x. I can start from x to predict y, because they are equally important. It doesn't have any difference why I say that this is a source or this is a target, because this conditional probability completely describes their statistical dependence between these two random variables. But now, instead of having this concept of computing the conditional probability, because it is getting quite complicated if this x is not a single scalar value, but if this x is a vector, then this density is defined not above a plane, but above a space that has a dimensionality of this n, what is the measure of the source, plus 1, what is the measure of the target. So I have n plus 1 dimension of the PDF source, of the domain of the PDF. And the PDF is then above this domain as a hypercircles. So it is much more complicated if the input source is a vector and not a scalar process. But we will show that by using a linear predictor, it gets quite easy to predict y from x. Why? Because a linear predictor can model not all the kinds of statistical dependencies, but linear dependencies. Linear dependencies between x and y can be modeled with a linear predictor, and such linear dependencies are called correlations. So whether the x and y source are correlated. So whether the source and target are correlated. So this correlation can be utilized to predict y value from x value. Okay? How we will do it? This linear prediction has a very simple form. It is simply a scalar product of row vector containing predictor coefficients and a column vector containing source of the prediction. So this vector x. So what was your body height? What was your size of shoes? Blah, blah, blah. I simply multiply these source vector components with corresponding weights. So actually this alpha 1 multiplies x1, alpha 2 multiplies x2. So it's like a weighted sum of your features. So here is your feature vector describing you as a person, and here are some weights that I use how each of the components contribute to the final prediction. And let's say that this final prediction is your annual tax return in 10 years from now. Okay, and then what I want to do, I want to minimize, as I said before, the variance of the prediction error as a function of alpha, because different choices of this weighting, alpha 1, alpha 2, would give me different predictions. And definitely, by selecting the best possible choice of alpha predictor coefficients, alpha 1, alpha 2, it is a choice that gives me the least variance between y tilde and y. So what is the least variance of prediction error? Okay, so our task is to find alpha vector that will minimize the variance of prediction error as a function of parameters, or we can say predictor coefficients. So this alpha dash is the one that really minimizes this variance. Okay. One thing I have to stress is that this set of coefficients, alpha, is a constant set of coefficients. It is not something that I will change for one source vector and then use another set of alpha for another source vector. I will use the same set of predictor coefficients for all of you. So it doesn't matter if it is first calling in the first row or calling in the second row.
I will use the same weights to predict their target annual tax return. Okay? And for that reason, this alpha must be like a compromise. The best possible set of coefficients that is good enough for all of you, that fits all of your statistical properties between your sources and your target. Okay? And it can be shown that the predictor that minimizes this expression, that minimizes squared prediction residual, such predictor must satisfy the following condition, following equation. Equation says that in order to be optimum, this alpha must satisfy that the error, prediction error, must be orthogonal to prediction source. It is so-called orthogonality requirement. So only then the predictor is optimal. If the prediction error, so that is the difference between each predicted value y and corresponding prediction, y tilde, so this is E. This E as a scalar value, scalar error, when multiplied with the source vector used for prediction, if I find the expectation of this E times source vector, the expectation must be zero vector. Okay, so this E is simply the difference between y and predicted y. So this alpha dash transpose times x. How can I interpret this value? So this alpha transpose is this row vector of the prediction, because I would say that it is a column. So alpha is a column vector. But if I want to do the prediction, I transpose this column vector such that it becomes a row vector and multiply this row vector with a column of input source vector. Okay, so this alpha transpose times x is actually the prediction y tilde. The difference between y and y tilde is the error. Since this is a scalar value, I can rearrange this second part, because transposition of a scalar value is the same as the original scalar value. What I'm saying is this optimum alpha transpose as a row vector times x as a column vector. I know that this is a scalar value equal to epsilon tilde. Okay? And since this is a scalar value, I can write also epsilon transpose tilde is the same as epsilon tilde. And according to the rule of transposition, if I have to transpose this expression, then I have to rearrange the order. So it is then x transpose times alpha 2 times transpose, and that is alpha. So it is the same as having x as a row, x transpose as a row, and alpha as a column, Because it is first times first plus second times second, blah, blah, blah. So it doesn't matter if I write it this way or that way. So this epsilon tilde is as alpha tilde times x as a vector, what is the same as x transpose times alpha as a column vector. Okay? Now I have to find how to solve this and to find alpha from this equation. Okay, because if I would insert this E into this expression for expectation, this E is obviously a function of alpha dash, the optimum set of coefficients. So I substitute this E here. Okay? So the expectation of, as I say, x as a vector times E. So x as a vector, and this was the E. E was y minus x transpose alpha dash. And then according to properties of expectation as an operator, the expectation of a sum is sum of expectation. So we have two terms here. So it is expectation of x times y, first term, minus expectation of x times x transpose
alpha dash. Okay? And that should be equal to 0 vector. That must be equal to 0 vector. Okay, and now I will try to rewrite this equation by recognizing that this equation here actually is nothing else but this matrix equation described with phi xx and psi xy. Okay, so how can I come to this? It is by simply, so I have this expectation of x times y on one side of the equation, and then I say it is equal to expectation of x times x transpose times alpha dash, Okay, and now what is random here? Random are x and y, but alpha dash is a constant vector that I am trying to find. So expectation of some random vector, whatever, times constant is the same as if I would extract this to the right side, because this is a vector. You must remember this is a vector, so I cannot put it in front of the expectation. So I must have the right order of multiplication. And this here is a matrix. This matrix is this phi xx. Why? Because it is a expected value of something that looks like this, like a column vector x times a row vector x transpose. So I'm trying to find the expectation. It is called outer product. So not inner product, but outer product. If I would multiply a row vector with a column vector, it is the inner product or scalar product. But if I would multiply a column vector with the same vector but transposed as a row, it is outer product. And how do I do this outer product multiplication? Using the same rules, I will do matrix multiplication. Just to show you one example, so suppose that I want to multiply 1, 2 times 1, 2. Okay, then first row, first column, 1 times 1. First row, second column, 1 times 2. Second row, first column, 2 times 1. Second row, second column, 2 times 2. So what I get is a matrix 2 by 2 with these values. 1, 2, 2, 4. So there isn't any problem in finding this outer product using the same rules that you use for matrix multiplication. And what I have to do is I have to find the expected value of such outer product. So this phi xx is nothing else but the expectation of this outer product of what? Of source vector. So source vector multiplied by the same source vector transposed. So this is this phi xx. Expected x times x transpose. Okay, so it is a matrix of dimension. If I denote this dimension with p, it will be p times p matrix. P times p. So this small p will be used to 1, blah, 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 up to small p. It will be the dimension of the source vector. So what I get is a matrix phi xx of dimension p times p. Okay? And the same way I do it for the this term here, because this term here has a vector times a scalar. And I will denote this expectation with psi xy. Okay, so psi xy would be equal to expected value of a column x, source vector column x, multiplied with corresponding scalar target y. In this case, I can put target in front of x or after x, it doesn't matter because it is a scalar value. Okay, so it is the expectation of source times target. Okay, and now I have everything I need, because I have the original orthogonality requirement expressed as a Cxx times alpha. So I said before, this alpha can be extracted, and this is phi xx. And this here is psi xy. So I write psi xy as a column vector. It has dimension 1 to p, is equal to phi xx, which is p times p matrix, times alpha 1, alpha 2, blah, 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 alpha p. So this is the column vector alpha dash, the optimal column vector alpha dash. This is this one. So Cxy is equal to phi xx times column vector alpha dash, in a matrix form written as this. And now the only thing I have to do is to find the solution of this linear problem. And this solution for I dash, so Cxx, phi xx times alpha dash is equal to psi xy. If I want to find this alpha dash, I have to multiply from the left side with phi x to the minus 1, to the inverse of phi xx. And in this case, these two would get an identity matrix. This would cancel, and I would get my solution that this alpha dash is then phi xx inverted multiplied with cxy. So this is the optimal predictor. Minimizing sigma e squared. So this is the expectation of the difference, y minus y tilde squared. So the optimal predictor that minimizes the prediction error variance is the one that is found by this simple matrix problem, linear matrix problem. So alpha dash, the only thing I have to do, I have to compute this phi xx matrix, I have to invert it, and multiply this phi xx to the minus 1 with cxy. So this column, this cxy, it describes correlation between target, y, and individual components of the source vector, x. So that is the reason it has dimension column vector p. So the first component is the correlation of the first source component to the target, second source component to the target, blah, blah, blah. While this matrix phi xx is actually a covariance matrix of the source, because it describes correlation between individual components of the source vector. So what are the correlation between the first component of the source to the first component? That is its variance. What is the correlation between the first and the second, first and the third, blah, blah, blah. So this matrix phi xx is nothing else but the correlation between each individual pair of the source vector. Okay? This linear prediction that we have described here is actually closely related to regression analysis. And this regression analysis was derived from the so-called least squares method. The method of least squares was introduced in 1805 or 1809 by two mathematicians. One is Legendre and the other is Gauss. Gauss used it or simply came up to this theory of estimation, least square estimation, from the task of analyzing the orbit of celestial bodies. In particular, Gauss was concerned in predicting the trajectory of dwarf planet Ceres. So this dwarf planet Ceres, at that time they had telescopes and they could compute the position of this planet quite accurately. And they had a table of this observed position. And what Gauss tried to do is to calculate parameters of trajectory of this celestial body from its observation. And for that, it used this idea of minimum squared approximation. So what are the parameters of this elliptical trajectory of this Ceres dwarf planet? If I know the observation today, each month, whatever, each year, and that was the problem he was solving. And actually, he wrote it in a paper, let's say, in a written text. It was written in Latin, Theoria motus corporum celestium sectionibus conicis solem ambientum, but it was published only in 1809. And while the other guy, Adrien Marie Legendre, he already published this idea in 1805. And it was only due to this late publication that this idea of least square is contributed as the first inventor to Legendre and not to Gauss. Although the Gauss started on this problem much earlier in 1801. Okay? So he was trying to use this method to predict this motion of celestial bodies. And now we will introduce, we have only 15 minutes, the concept how to do this linear prediction in the context of this least square estimation, but we will use it to predict. Let's assume that I know the last p values of my signal. I know the xn minus 1, xn minus 2, up to xn minus p. I know the last p samples of my input signal. And what I want to predict, I want to predict a current sample, x of n. So if there are any correlations between neighboring samples of the signal, then supposedly or hopefully I will be able to predict this x of n from its past samples. So if the signal is correlated, then I should be able to have some good estimate or good prediction what will be the current sample x of n if I know the past p samples xn minus 1, n minus 2 up to n minus p. Shown graphically, so assume that this is a signal, this black, and this range, red with red bars, are those previous time samples, x minus, I guess 10 or 9, I think it's 10, x minus 10, x minus 9, x minus 8, blah blah, and up to x minus 1. And I'm predicting x of n where n is 5. So current n is 5, and I'm trying to predict x of 5 from x of 4, x of 3, x of blah blah blah, up to x of minus 5. So these are the source values that I'm using to predict the green target value. And I will do it by simply applying a linear predictor. So this value, x of 4, so this is actually n minus 1, x of n minus 1 will be multiplied with alpha 1. N minus 2 will be multiplied with alpha 2. And the last one is this n minus p, p is 10 in our case. So x minus 10 will be multiplied with alpha p, that is alpha 10. And these products are then simply added up, accumulated, and what gives me a sum is then a prediction of the target. The target being the same signal x, but for the time sample n. So I am predicting x of n from previous p time samples. And this prediction is shown graphically here. So this violet or whatever color is the predicted value of the actual green sample. I can also compute the difference between these two, and this difference is the prediction error that is shown in the last graph. So I subtract from the actual value, I subtract its prediction, x tilde of n, and I get the error E of n. Okay, so that is the idea how this linear prediction can be easily applied to time sequence, to time signal. And that it works quite well, it is shown here for one short segment of a speech waveform. The green line is the actual waveform of the speech for one voice sound, for one vowel, like A, O, E, I don't know which one. So this is the green solid line, and while the dotted, red or whatever color that is, line is the prediction of the green curve from only 10 previous samples. So I use 10 samples of the green line, I assume that I know them, and I predict the first next value. And it is shown with this dashed red or whatever color. And I can subtract these two. I can subtract the actual waveform minus its prediction. And in the same scale, I would get prediction error. So it is shown in the same scale of y-axis. So you can see that the prediction error is much smaller than the actual signal that I'm being predicted, that is being predicted. So it means that the prediction is quite successful. I can really predict new sample from the previous 10 samples. Okay? And now we only have to apply this concept that we have introduced for the general vector linear prediction to this case where this vector is not any vector. So before we had this was your body height, this was your shoe size, whatever. Now these elements of the source vector are not some features, randomly chosen features, but these are actually previous samples of your signal that is used for prediction source. So this is xn minus 1, xn minus 2, blah, blah. So I applied the same theory, but for this particular source vector and for this particular target, scalar target. So our scalar target is x of n, and our prediction source is this vector xn minus 1, xn minus 2, up to xn minus p. Okay? And first of all, I am trying to find this matrix Vxx. And that was this covariance matrix that shows the correlation between each individual pair of source components. And as I said before, it is simply the expected value of x as a column vector times x as a row vector. So this is a source vector as a column vector. This is a source vector as a row vector. And by multiplying this column with a row, I get a matrix that is of dimension p times p. So the first element is xn minus 1 times xn minus 1. Its expectation must be found. Okay? Blah, blah. And now, since this here involves expectation, I want to apply approximation of this expectation based on sample mean. So instead of using the expectation, I would use like what is the average value of this outer product. So I will use this average value as an approximation of expected value. And such simplification, such assumption that I can use this sample mean instead of using expectation is valid only under certain conditions, and this is condition of ergodicity of the process. So this process must be ergodic, and that means that the expectation can be approximated using the time average over all indices, time indices n. So I will use averaging. I will average these outer products instead of using the expectation, but that is valid only under the assumption of ergodicity of this process. We will not go further into details of this definition of ergodicity, but it actually defines that this sample mean is a good approximation of the expected value. Now, so the analog problem is for the column Cxy. So the Cxy is the expectation of x times, like a vector, times the target y. In our case, this is the source, xn minus 1 up to xn minus p, and the target is x of n. So I have to find the expected value of this product of column vector and scalar value x of n. Again, instead of having the expectation operator, we will substitute this expectation operator with simple mean. We'll compute the average value of such products over all n for all vectors that we have. And the final expression is then shown here. So phi xx is a matrix P by P whose elements are defined here, as well as Cxy is a column vector whose elements are shown here. Just to remember how we came to this, just to be more illustrative. So originally we had expectation, this was here like a x of n minus 1 up to x n minus p. Okay? And it was multiplied with the row vector, with the same row vector, x n minus 1 times x n minus p. And I understand this is the matrix of the measure p times p, whose elements are expected value in the first element of what? Of the product, x n minus 1 times x n minus 1, sorry, x minus 1, x minus 1. Okay, so the expectation of the first component of the source. Then the second element is expectation x n minus 1 times second column, and that is x n minus 2. Okay, blah blah. And goes up to n minus 1 times n minus p in the first row. In the first column, I have the expected value of x n minus 2 times x n minus 1. Okay, second element, expected value x n minus 2 times x n minus 2. And since multiplication is a commutative operation, it doesn't make any difference, so these two values are equal. It doesn't matter whether it is first n minus 2 times n minus 1, or it is n minus 1 or times n minus 2. So these are equal. And that means what I would get is a symmetric matrix. So the covariance matrix, this Pxx, must be symmetric matrix, and this expectation that are part of the matrix, I can write that this Pxx, sorry, so Pxx can be formed as with elements Phi xx 1, 1, Phi xx 1, 2, up to Phi xx 1, p, and in this direction Phi xx p, 1 up to Phi xx p, p. Ideally, these elements Phi xx of I, j is nothing else but expectation of x minus I, sorry, n minus I. X of n minus I times x of n minus j. Okay? That is the element, for example, this one, I substitute A is equal to 1, I is equal to 1, j is equal to 1. Okay, and this expectation is approximated with a mean. So I will say it is approximately equal to sum over n of such elements, x n minus 1, x minus I, x n minus j. So these elements of covariance matrix phi xx will be computed by averaging this correlation, and this is a correlation of the source, but shifted by I samples on the left side, by j samples on the right side. Okay. Now that I have this matrix phi xx, the same is done for the column psi xy, but now I have such a sum, because this second term is always x of n. It is always correlation to the target. Target is x of n. So as written in a general form, I can still use this notation phi of I comma, okay, it is k here, not j, sorry. So I can still use this, the same notation, phi of I comma k equal to 0, because this second n minus k is in this case always n minus 0. The second part is always equal to x of n for the psi vector. So the elements, the only elements that I have to compute are these elements, this phi, for combination of I and k from 1 to p, but also for k equal to 0. So not only from 1 to p, but for k from 0 to p, for I from 1 to p. Once I have these values, I can construct the matrix. So this here is this matrix exactly as I have written on the whiteboard. So this phi 1, 1, phi 1, 2, blah, blah, up to phi pp. And in the column on the right side, in the psi xy column, I have the same elements, but 1, 0. So I is equal to 1, but this k is equal to 0. 2, 0, up to p0. Okay, and this is the general form of this element phi of I comma k, I comma k. It is simple average of these two vectors that are shifted by I samples or by k samples. This factor 1 over n exists here on the left side, but also the same factor 1 over n exists in psi vector on the right side. So it can be omitted because it is cancelled. So you don't have to really divide with the number of vectors, number of samples. You can omit this constant term 1 over n. It is cancelled in this matrix equation. And finally, the only thing we have to find is invert this matrix, and we will have the optimal prediction vector as a product of phi xx inverted times psi xy, and that is this vector here. That is the optimal predictor vector alpha dash. As a final discussion, a predictor with p coefficients can model correlation only up to p samples backwards, because the order of the predictor is p. It doesn't go further in the past than p samples. So it can model correlation that are spanning at most p samples to the past. And obviously or logically, if I increase the order of the predictor, the error must necessarily reduce. If I add one additional sample from the past, necessarily the prediction error must reduce. So monotonical reduction of error is resulting from increasing the prediction order. Linear predictor has a very simple implementation, and we will show it in the next week. That is actually a digital filter that has a finite impulse response. So it is called FIR filter, finite impulse response filter. So I can do the prediction by simply filtering the input signal through this prediction filter, prediction FIR filter. I will just show the last slide. So this here, this inner structure is this P of Z predictor. So at the input we have the input samples, X of n. These here are delays by one step. So this is like a delay element. And the output of this delay element is the signal value from the previous step. After another delay element, the output is signal value from two steps in the past. Blah, blah, blah. After the last one, X of n minus P. And what I do, I simply multiply these delayed signal values with corresponding predictor coefficients, alpha 1, alpha 2, alpha 3, up to alpha p. I add up them together, and what I get x tilde, I get the prediction of the input vector, or of the input value x of n. So this input value x of n is then predicted with x tilde of n. If I take the difference, I have the error, E of n. And the system that computes the error, this outer system, will be denoted with A of z. It is also an FIR filter, while this inner system will be denoted with P of z.